Hello everyone, and welcome to this video lecture about the free vibrations in strings. In this video lecture I will discuss the general theory, and in the next lecture I will then do an example. So what I've shown you here already is the equation of motion for vibrations in strings, as well as the boundary conditions for the specific case that the string is fixed at both ends. Also, for free vibrations we now need the initial conditions. So the initial conditions describe the initial shape of the string as well as the initial velocity profile of the string. In the previous lectures we derived the expressions for the natural frequencies, omega n, and we found them to be n times pi times the square root of t divided by rho al squared. We also found an expression for the natural modes, Vn, as a function of x, and they were equal to alpha times the sine of n pi x divided by L. And there are infinitely many of these frequencies and modes. Then in the lecture on orthogonality of these modes, we have derived that these mode shapes are mass normalized for alpha equals 2 divided by rho al. Okay, so this is the specific value for alpha that we will work with. Also, we found the orthogonality conditions that when I is not j, the following rules holds, that the integral of vi times vj dx is equal to 0, and that the integral from 0 to L of vi prime times vj prime dx is equal to 0. Alright, now I need to explain the general strategy with which we are going to solve for free and forced vibrations, and this is based on modal analysis. And for that we are going to need the so-called modal expansion. And the idea of this expansion is very similar to that of discrete systems, in the sense that we are going to write the solution of the displacement field in terms of all the natural modes. And in this case there are infinitely many, so I will write it down as this infinite sum of I is 1 to infinity of a mode shape vi that describes a shape times a modal coordinate eta I as a function of time. So eta I rd is a modal coordinate that basically describes in time how the corresponding mode shape vi behaves. Okay, let's substitute this modal expansion into the equation of motion. For the first term we get this infinite sum of rho a times vi times eta I differentiated twice with respect to time, minus, and then another infinite sum of t times the second derivative of vi with respect to x times eta I itself. And this should be equal to 0 for free vibrations. So what I'm going to do now is I will multiply the entire equation by vj and then integrate from 0 to L. So I keep this infinite sum, rho a, and now I integrate from 0 to L, and then I have vj vi dx times eta I double dot minus infinite sum of t times the integral of vj times vi double prime dx eta I, and this is equal to 0. Now this second integral I will manipulate using integration by parts. So the first term I will just write down again quickly. So that stays the same. We have Vj, Vi, dx, eta I double dot. And now if we do integration by parts and apply the boundary conditions that Vj is 0 at 0 and L, all right, then using this integration by parts, we can rewrite it to plus the infinite sum of t, and then we have the integral of Vj prime, Vi prime, dx times eta I. I did the same integration by parts in the previous lecture. Okay, at this point, we can use the orthogonality conditions that both these integrals that appear are 0 whenever I is not j. So that means of these infinite terms, this infinite number of terms in the sum, all contributions are 0 except for the case that I is equal to j. And then for that specific situation, we have done the mass normalization of the modes such that the term in front of eta I double dot equals 1, and the term in front of eta I itself equals omega n squared, omega I squared. So we get from this, using orthogonality, that eta I double dot plus omega I squared eta I is equal to 0, for I is 1, 2, all the way to infinity. So in fact these represent the modal equations of this continuous system. Let me write it down. These are the modal equations. And as we have seen for discrete systems, these modal equations are of the form of a single degree of freedom system. So that means that its solution, in terms of the initial conditions for eta I, is quite easy to find. This is simply eta I as a function of time equals eta I at 0 times the cosine of omega it plus, and then we get eta I dot at 0 divided by omega I times the sine of omega it, where the initial conditions for the modal coordinates eta I and eta I dot at 0 are still unknown. So the challenge is to find out what are eta I at 0 and eta I dot at 0. Okay, in order to solve this, we are going to look back at the initial conditions themselves, right here, and we substitute the modal expansion into this initial condition. So we write down that v as a function of x at time is 0 is the infinite sum, I is 1 to infinity, of vi as a function of x times eta I at 0. And this must equal v0 as a function of x. Now I'm going to multiply both sides of the equation by rho a vj, and I integrate. And as a result, we get this infinite sum of rho a, and then the integral of vj times vi times dx, eta I at 0, and this is equal then to rho a integral of vj times v0 dx. Now again, by means of the orthogonality, all terms in this sum are 0 for I not j, and for I is j, this term is equal to 1. So from this, it follows immediately that eta I at 0 equals rho a, the integral. Now let me write down vi, since I is j, times v0 dx. So this is the way in which we determine the initial condition for the modal coordinates. Now, in a very, very similar way, we can specify the initial velocity. So that would be the infinite sum of vi of x times eta I dot at 0. And this is a known function, a prescribed function, v dot 0 of x. And by carrying out the same procedure, we find that eta I dot at 0 is the integral rho a times the integral of vi times v0 dot dx. So this is the expression for the initial velocity of the modal coordinates. Okay, so let me summarize the procedure. In order to determine the free vibration response of a system, we need its equation of motion, its boundary conditions, and initial conditions. We first derive expressions for natural frequencies and corresponding modes, and we make sure to mass normalize the modes. Then, the solution in terms of the modal coordinates is very simple, and it's given here, all right? Where eta I and eta I dot at 0 are given by these box expressions over here. So we solve for these initial conditions, substitute it in the general solution, the solution for eta I is a function of time, and then we back substitute this into this modal expansion itself, and that then finally gives us v as a function of both x and t. So I hope that this gives you a good idea of how to do this in general. In the next lecture, I will give you an example, also based on the same boundary conditions, but then I will specify the initial conditions. And that will give you a much better idea, hopefully, of how to do this in a specific case. So I hope to see you in that lecture again. Thanks for now.